Now let's talk about components of acceleration and circular motion. So the components of acceleration refers to decomposing the vector acceleration into tangential and normal components with respect to the velocity vector or the unit tangent vector. So the acceleration vector can be decomposed into one component which is tangential. Remember, this unit tangent vector is parallel to the velocity vector. So this part is parallel to the unit tangent vector, or it's parallel to the velocity vector. So we're decomposing it into one component that's parallel to the velocity vector, and then the second component that's perpendicular to the velocity vector. And we do this just using the doing the projection formulas that we've seen before. So this tangential component is given by the projection, and the normal component is given in the same way we found the decompositions before, which is subtracting off the parallel component after we find it by projection. We know from a previous example where somebody was driving around in a car that was speeding up and turning left, that phenomenon is true in general. The parallel component or tangential component of acceleration corresponds to acceleration along the path, meaning speeding up or slowing down along the path. The normal component corresponds to turning or changing direction. So to recap, if we want to find this decomposition of the acceleration vector, starting from a given position function, we would start by differentiating to find v of t, that's r prime of t, and then we would differentiate again, find v prime of t, the second derivative of the position, to find the acceleration vector. And then to find the tangential component, we would project along v of t. We have presented this as projecting along the tangential vector t of t, but it works to use v of t instead because they're in the same direction, and the projecting in that direction just depends on the direction. It doesn't depend on how long the vector is. It doesn't make a difference. And projecting along v of t is just simpler than projecting along t of t because you save a step of dividing by the length. So just a reminder that projection formula, this is the projection of the acceleration vector, and it's projecting it along the velocity vector, and the formula for that is the dot product of the velocity vector and the acceleration vector divided by the length squared. Do you remember which length we're supposed to divide by? We are going to divide by the length of the thing that we're projecting onto. And then that scalar gets multiplied by the velocity vector. Finally, to find the normal component, we would subtract the acceleration vector that we found in the first step, and then taking away the tangential component that we found in the second step. And the difference gives us the normal component. So that was just a recap of how to find that decomposition. For an example, suppose that a particle is moving so that its position is given by t squared t cubed. With that position function, let's try to find the decomposition of the acceleration into the tangential and normal components at the time t equals 1. Okay, when we differentiate, we find that the velocity vector is 2t, 3t squared. That's just the derivative of the position. If we differentiate again, if we take that velocity vector and differentiate one more time, we get the acceleration vector is 2, 6t. And the question is particularly asking about t equals 1. So we can plug in t equals 1, and we get v of 1 is 2, 3, and a of 1 is 2, 6. So we're trying to decompose the vector 2, 6 into components that are parallel and perpendicular to the vector 2, 3. And the answers are written here, but I'll work through the formulas. So A parallel, or the projection of A along V, is V dot A divided by length of V, I almost wrote an A there, length of V squared times vector V. All right, so looking at V and A, and taking their dot product, we get 4 plus 18. Two times 2 is 4, and 3 times 6 is 18, right? And then we'll divide by the length of V. So when we square the components of V and add them together, I have 4 plus 9. And I would have square rooted, but we're doing the magnitude squared, so that gets rid of the square root. So we end up with 22 over 13 times vector V, and vector V is 2, 3. So that's what's written here. So that's the tangential component, and in decimals it's about 3.38, 5.08. For the normal component, or perpendicular component, we subtract. So this 2, 6 minus 22 over 13, 2, 3. And you could do a little fraction arithmetic, put the first vector on a common denominator of 13, and work out what you get. I'll leave that for you if you're interested, but it comes out to be minus 1.38, 0.92. Do you know how we can check? How we can check our work? One way we can check our work is we can ask, is the normal component that we found, is it perpendicular to the velocity vector? It's supposed to be, right? So we can check and see if it is. So how would we check perpendicular? To check if they're perpendicular, what we can do is take the dot product and see if the dot product is 0. So we'll take the dot product an dot v and see if that's equal to 0. So we'd have minus 1.38, 0.92, dotted with the velocity vector, which is 2, 3. And if you work that out, then sure enough, we do get 0. So you can work that out or use a calculator if you want. Okay, so those are the components, and this is the acceleration vector of the moving object speeding up along its path. So like a gas pedal accelerating forward, and this is a vector to the side of the moving object turning. And if you plot this path, when t equals 1, this is at the point 1, 1. It's starting at 0, 0, and t squared is increasing and t cubed is increasing. So in general, it's moving up and to the right because both the x and y components both are increasing. And if you actually plot it, it looks something like this. It sort of curves up. I know I'm just hand drawing it. It's not very precise. If you draw it more carefully, it's not as curved as a parabola, but it's sort of reminiscent of a parabola. It's a similar shape. Anyway, so this thing is speeding up because there's our velocity vector. It's speeding up along the path, as we see from this acceleration, and that's not surprising. The x is going faster and faster. The y is also going faster and faster. So this is going faster and faster. So there's our A parallel that's speeding it up. And we also found that the normal component has a negative x direction and a positive y direction. So the A normal is pointing off to the side, pointing to the left and up, like this. Maybe I should move this parallel vector to be actually on the point. It makes the drawing fairly crowded. So I guess we'll just have the velocity vector sort of nearby like that. All right, so this is this part means that it's speeding up, and this normal part means that it's turning left. And that fits in with the general shape of this curve, which if you were driving on this road, you would be sort of bending or turning to the left. So that's what's going on with that decomposition. Let's look at some examples with uniform motion. So let's start with uniform circular motion. Uniform circular motion is a specific thing. We have a particle or an object of mass m moving around a circle of a certain radius with a constant speed. So that's what makes it uniform, is the constant speed. Then the position is given by the radius r times cosine of an angle, comma sine of an angle. And this angle is omega times t, where omega is some constant. If omega is a large value, then this angle is a large multiple of t, and that means that the angle is moving very rapidly as time goes by. If omega is very small, then the angle is a small multiple of t, and every second brings a very small increase in the angle. And the angle would move slowly. So this omega is directly related to the angular velocity of the motion. So that gives the position of the moving object. From there, we can figure out the velocity vector of it by taking the derivative. R is a constant and omega is a constant. So we just use a chain rule, and these omegas that are on the inside, they come out in front. From there, we can figure out the speed of this moving object. The scalar speed would be the magnitude of that velocity vector. We have a multiple r times omega as a scalar multiple, and then we multiply by the magnitude of this vector. But this vector is a unit vector. It has a sine of an angle and a cosine of an angle. If you want to go through the steps, you can square them and add them together. We'd have minus sine squared plus cosine squared, and the fact that there's a minus sign doesn't really make a difference. We just get 1. So that vector is a unit vector, and it's being multiplied by r times omega. So the speed is r times omega. And now one detail that I glossed over, but I'll say it now, is that we really want to take the absolute value of omega. Omega might be a negative number. If omega was a negative number, then that means that when our time goes up, we would have negative times it, the angle would be decreasing. So the angle would be going in the negative direction. So if omega is less than 0, then it's going in the opposite direction. It's a clockwise motion. And just in case the omega was negative and we're going clockwise, then we better put a absolute value to get the speed. So we can relate them. The angular speed or angular velocity omega is v over r. From this equation, v equals r times omega. So sometimes I guess v is called the linear speed. That's the speed that it would be going if it was going in a straight line, and the omega is the angular velocity. And they're related like this: v is r times omega, or omega is v divided by r. And then from there, having the vector velocity, we can now find the vector acceleration by differentiating again. So our omega is still a constant. It stays just a constant multiple. We have a chain rule with omega t on the inside, so we just multiply by omega in front, and the new omega joins the omega that was there, and we get omega squared. So we have r omega squared times minus cosine omega t minus sine omega t. The r cosine omega t, r sine omega t, that was our original position function, little r of t. So what's new is the minus sign and the omega squared. So some things to observe. The magnitude of this acceleration vector is r times omega squared, because the acceleration vector is r times omega squared times a unit vector. This vector here is a unit vector, and I guess I mentioned before that that one and the velocity was a unit vector, but I didn't write it on the slide, so I'll go ahead and write it. So we have a scalar multiple times a unit vector. That means the magnitude is just that scalar, r times omega squared. And another thing to notice is that the acceleration points toward the center of the circle. That's maybe the most important fact. What's going on here is that in our circle, if you're at one of these points, then the position vector is pointing from the origin to that point. R of t is a position vector. And now what we're seeing is that the acceleration vector here, the acceleration vector has minus omega squared r of t. So it's pointing in the opposite direction. It's pointing in the opposite direction to r of t. And it doesn't matter if omega is positive or negative. Either way, omega squared is positive, and then minus omega squared is negative. So this is a negative multiple of r of t, and that means that the acceleration points in the opposite direction. So r of t is pointing from the center out, and the acceleration is pointing in the opposite direction, in towards the center. One upshot of this is that in order to have this kind of acceleration, there must be some kind of force given by Newton's second law. Whatever force it is, it must be the mass times this acceleration that we found. So there must be some force pointing in towards the center of the circle. Do you know from physics the name of a force that pulls an object towards the center of a circle? That would be the centripetal force, or a centripetal force. Centripetal force. And there isn't just one specific centripetal force. It could be anything. There could be a rope tied to the middle and tied to the object and swinging around, and the rope could be pulling, or it could be gravity, or it could be an electric force between charged particles, or it could be magnetic or whatever. Any type of force can pull an object towards the center and cause it to have uniform circular motion. But whatever force that is, a force that pulls something towards the center of a circular motion is usually called a centripetal force. So just for practice with that idea of uniform circular motion, suppose that we have this lake, which is not exactly circular, but it's roughly circular, and a lighthouse is in the middle of the lake, and it's turning, and it's shooting out a beam of light. Like this, it's shooting out a beam of light to the shore of the lake. And that beam is moving around the shore of the lake. So we're curious about the velocity vector of the beam, or the spotlight on the lake shore. At which point A, B, C, or D is the velocity vector of the beam most parallel to vector J? You can pause the video and think about it. The answer is point B. At point A, the velocity vector looks like that. At point B, the velocity vector is pointing up. At point C, the velocity vector is pointing sideways. And at point D, the velocity vector is pointing sort of southeast. So B is the answer, where it's most parallel to J. Now we're wondering about the same question with the acceleration vector instead of velocity vector. So there's the same setup with a lighthouse. And now, when is the acceleration vector of the beam most parallel to J? You can pause the video and think about it. This time the answer is C. So remember what we found for uniform circular motion. This has constant angular velocity. Now the lake is not exactly circular, so that's going to throw things off a little bit, but we found for uniform circular motion that the acceleration is pointing in towards the center. So in point A, it'll be pointing in, the acceleration vector will be pointing in. At point B, it's pointing in towards the center. At point C, it's pointing in towards the center. At point D, it's pointing in towards the center. And all of these are tilted or horizontal, but point C, it's vertical. The acceleration vector is pointing up towards the center of the lake. So that means that at point C, the acceleration vector of the beam is most parallel to J. Now, to close this out, we're going to go a step further and we're going to look at non-uniform circular motion. Uniform circular motion is what we just looked at, and that had a position function with a constant angular velocity omega. But what if omega is not constant? What if omega is increasing? So the example that's written here has angular velocity equal to t. So it's increasing when t increases. In that case, then omega times t would be t times t. It would just be t squared. So we're going to look at a position function given by cosine of t squared, sine of t squared, with a radius r. In this case, we can figure out that the velocity is the derivative of that, with a constant multiple r times minus sine of t squared. So I have minus r sine t squared, and the derivative of the inside function is 2t. Here, r sine t squared, we have a constant multiple r. Derivative of sine is cosine. The inside function stays the same, t squared. and then we multiply by the derivative of the inside function, which is 2t. So I suppose I should say that I was using the chain rule. We used the chain rule there. With that velocity vector, then we can go on and find the acceleration vector. So if you would like to, for practice, pause the video and work it out for yourself. Or if not, you can at least take a moment and think, what rules are we using? Which differentiation rules are we using in this problem? Since we have a t multiplied with another function, I have two non-constant functions multiplied together. When we have a product of functions like that, we have to use the product rule. So I'll differentiate the t and leave the sine t squared alone. And then we'll leave the t alone and differentiate the sine t squared. So I have minus 2r sine t squared when we differentiate the t. And then for the next term, we'll leave the minus 2rt alone and differentiate the sine t squared. To differentiate the sine t squared, we have to use a chain rule. So this was a product rule. And next we have to use a chain rule. And that chain rule is the same chain rule that we did to get from the position to the velocity. So I won't write down the steps, but when you do write down the result, you get what's written here for the acceleration vector. And now on the next line, we've just simplified it a little bit. Our first term matches with the velocity vector. We're just grouping terms together. So we have the velocity vector but missing a t. So 1 over t v of t and 4t squared times r of t. So this is what we found for our acceleration vector. And in fact, we don't need to do any projections at this point. We've already decomposed it into one component that points along the direction of motion in the direction of v. It is a scalar multiple of v. And a second component, the 4t minus 4t squared r of t, which points in the direction of r, which is towards the center of the circle. And we know that v and r are perpendicular because it's a circle and the radius is perpendicular to a tangent line. This actually does give us our decomposition into a tangential part and a normal part. The 1 over t v of t is pointing in the direction of motion, and it's pointing forward because 1 over t is a positive number. And minus 4t squared r of t is pointing towards the center. The r of t is pointing out, and minus r of t is pointing in. The 4t squared makes a scalar multiple, just like the 1 over t is a scalar multiple. And if you think about it, as t grows and grows, if t just keeps going for a long time, this 1 over t is dying down. So that scalar is going to 0. But on the other hand, the velocity is getting faster and faster. The velocity is growing. So in combination, the 1 over t shrinking and the velocity v of t growing balance out. And this tangential component of acceleration actually stays the same. So this keeps on accelerating forward at the same rate always. But the pull towards the center grows quite a lot, actually. It grows like t squared, so that's kind of exploding. So as this thing goes faster and faster, it takes more and more force to hold it in. And Well, this plot just demonstrates the acceleration vector pointing forward of the center, and you can see the components projected onto there. I'll go back to the previous slide. We could have found the same thing by working out the projection. We could have taken this first line that was written for the acceleration before we started grouping it into two separate vectors, and we could have gone through the projection method. Just in this example, it turned out that you could just group some terms together and get the result. So we just jumped to that. Well, that's it. All right, thanks for watching. Bye.